Hi, my name is Robert Kerdman, and this is my Lab 2 projectile motion. So, for this presentation, I'm going to start with the introduction. I'm going to go into the modeling that we did, the experiment itself, the coding, and then just a discussion and a conclusion. So, to start with the introduction, the purpose of this lab was to compare the projectile motion of an object, like its real projectile motion, compared to its predicted computational trajectory. And we did this by using drag force for the predicted and no drag force for the realistic. We threw a paper ball of mass 3.1 grams, and for our surroundings, we defined that as the external forces such as gravity, drag, etc. And we recorded the position of the ball using the tracker program, and we modeled it via GlowScript. Here is the math that we use to calculate the different forces. So as you can see, we use the velocity update formula to find the drag force, and we use the position update formula to find the force due to gravity. The procedure was to take a video of the trajectory of the thrown paper ball, upload that video to Tracker, and track the movement frame by frame, and then we created a computational model to predict the projectile trajectory of the object with and without the consideration of drag force. Then we put the data into graphing software. We just used Excel. So on the left, you could see our video, or a snapshot of the video. That point marked is the maximum height that the ball went. So the initial conditions we used were time started at 0 and position started at 0, 0, 0. And then we used average velocity, which we calculated in the previous slide. Here's our GlowScript code. This is the code without drag. So as you can see, the duration of our experiment was 0.8 seconds. The net force was just Fg, because we are not using drag. Under that, you can see the position and velocity update formulas. The initial conditions we could see on the right side with the mass of the ball and the initial velocity and position. And then we use delta t as 0.0333 because the camera records in 30 frames per second. With drag, we could see that net force is added, Fg plus F due to drag. And we set the proportionality constant to 0.01. So here are our results. We could see that the Y position follows the expected trajectory, and the X position also follows the expected trajectory because there's no external forces in the X position. So the model position makes it shows that the model with drag shows that the ball went less distance than without the drag. This is because the drag force opposes momentum, so with drag it goes less distance. Sources of error: the camera did shake a little bit as we threw the ball, and this made the axis shift difficult when tracking the position. And the B value isn't entirely accurate, and that impacts trajectory. Our computational drag model did demonstrate terminal velocity, and at F net equals 0 at some point in the model, illustrated by a constant velocity. If the object were thrown straight up with the same initial speed experiment, what would the time it takes to reach the ground be the same or different than in your original experiment? So the time the object takes would take longer because if you use the magnitude of the initial speed and throw it straight up in the y direction, then it would take longer because the magnitude of the initial speed is greater than the initial velocity and the y component of particle motion. Thank you very much.